Hello friends, welcome to Geology Concepts. In this video we'll discuss fluid inclusions. There are questions that has been asked in GATE examination. This question is you see here, it was asked in 2012 examination, and this question here was from the GATE 2018 examination. So we'll discuss the concept of fluid inclusions and understand how logically we can solve these two questions. So let's begin. Now, fluid inclusions are basically cavities in which some amount of liquid and some amount of material is trapped during the formation, like in the ore processes that are related to igneous activities or hydrothermal activities. In that we find these fluid inclusions. Now, the composition of material that is present inside the fluid inclusions can be pure water. Now, water can be in two phases, means one can be the vapor phase of water and another is the liquid phase of water. There can also be brines of various salinity. Brine means is a mixture of salt and water, mainly it is NaCl, which is present in the liquid, and it can also be present in the solid form, which is called as halite. Now, there can be gas or gas bearing liquids, means a liquid in which there is a gas. As you can see in this figure here, there is this bubble, right, vapor bubble, that is gas, and the liquid, this whole thing as you see is cavity. There can be silicate, sulfide and carbonate melts also, but in a very small amount. Mostly it is water, CO2 and NaCl. Now, fluid inclusions are formed in the ore depositing systems, like in the igneous processes of ore formation and hydrothermal processes. Now, based on the type of inclusion, it can be a LV inclusion in which the liquid is dominating and vapor is very, let's say, in as compared to liquid, it is in the small amount. We call it LV inclusions. There can be VL inclusions in which the vapor bubble is the dominating thing and liquid is very less in the cavity or in the inclusion. Then there is aqueous carbonic fluid. In carbonic we have CO2 vapor, CO2 liquid and aqueous, that is water. Then we have LVHS inclusions in which there is liquid, vapor, halide, sylvite, all are present inside this cavity. As you can see in the crystal form, here you have NaCl or sylvite. Sylvite is KCl. So in a small amount sometimes KCl is also present, but dominating salt that is present in inclusions is mostly NaCl. And as we know, NaCl can dissolve in liquid, right, in any proportion. So in the liquid, if there is NaCl, it will have some salinity. So we calculate this salinity value also. So we'll see what is the motivation behind studying these fluid inclusions. So again, the process of studying this is called as microthermometry. Obviously, from the word thermometry, we can understand that we are looking towards calculating the temperature of the formation of these fluid inclusions, right? And it is done by heating and freezing the sections on a specially designed microscope, as you see here, right? This microscope stages, and we can cool and heat the samples, right? And can measure the temperature, right? Cooling is mostly done by liquid nitrogen. Heating can be done by any light source. And in a very controlled environment, we try to understand what we try to understand here, the trapping temperature. Now, trapping temperature is the temperature at which the all the materials was trapped inside the inclusion and it became a closed system. We can also determine salinity of inclusions. Salinity means the amount of NaCl and KCl present, and it is always, this salinity is always given as equivalents of NaCl, right? Like जैसे there is this, the hardness of water is given in terms of calcium carbonate. Similarly, salinity is always given in terms of equivalents of NaCl. Now, fluid inclusions, the study of fluid inclusions has some assumptions associated with it, because whenever you are trying to study something, you have to make some assumptions. So the assumptions are very justified. First, that fluid is homogeneous. Homogeneous means if we keep on heating the fluid, it can convert into completely homogeneous phase. Let's say it is completely liquid, or it can be a completely vapor homogeneous phase in which there is no heterogeneity. Then it has a fixed volume. Now when I say fixed volume, it means that the cavity is fixed and its size will not increase or decrease with the changing condition around it. Okay, so volume is fixed. Now we also assume it to be a closed system. That means nothing is going inside and nothing is coming out of this inclusions. So the material which is present inside the inclusion is fixed. So we can say that the mass of this is fixed, right? Because it is a closed system, we can say the mass, the matter is not going inside, not coming outside the fluid. So the mass is fixed. So this means if anything has a fixed volume and a fixed mass, we can say that the density of this fluid inclusion, or the density of the material inside the fluid inclusion, or you can say more generally, you can say the bulk density will be fixed. Think of it like a space which has a fixed volume and a fixed mass inside it will definitely have a fixed overall density, which you call as bulk density. Why I'm saying well, because inside it can be in the form of bubble, liquid and solid, or all of them together. But overall density means individually liquid can have some density, vapor can have some density. Obviously the salt that is precipitated can also have different density, but overall bulk density will be same, because we have assumed the fixed volume constraint and a closed system, right? Another assumption is that the effect of pressure around the inclusion is not significant or are insignificant. That means the pressure outside the bubble or outside the cavity, will have no effect on the workings of the inside of the cavity. So it is completely isolated from the outside pressure. But temperature can change. If we change the outside temperature, obviously the temperature of this cavity or the constituent inside this cavity will change. And we also assume, the assumption is that because we know the origin of this fluid inclusion, that means we know the depth at which and the setting in which this inclusion is found. So what we are trying to say that we know the pressure at which it has found, or you can say the trapping pressure. So this is the basic assumptions. Okay, and now we can proceed to understand the concept behind this. Okay, so motivation is clear. We are studying this because we want to calculate the trapping temperature and the salinity at that point of time when it was forming. Also, these are the assumptions. Basically, we have to keep in mind that the density will remain constant. This is very important. We'll use this. Now, before going into the concept, we'll be coming across this phase diagram quite a number of times. So let me just, this is a very common diagram, most of you will know it, but let me just give you a brief overview of this. This is a phase diagram for water, where you see on the y-axis is the pressure in atmospheres, temperature is in degrees Celsius. On the earth's surface the pressure is 1 atmosphere, and we know this is ice, this field is of ice, this field is of liquid, or you can also write water, and this is your vapor form. So the interface between ice and liquid is this red line here. Now this line at 1 atmosphere, you can see at 1 atmosphere, if you increase the temperature, ice will convert to water at this point, and we know that is 0 degrees Celsius because pressure is fixed at the surface of earth, which is 1 atmosphere. If we change the pressure, then ice will not convert into water at 0 degrees Celsius. If you increase the pressure, it will convert at some negative temperature, and if you decrease the pressure, it will convert at some higher temperature than 0 degrees Celsius. So this 1 atmosphere value, just when we say the water freezes at 0 degrees Celsius, the basic assumption is that the pressure is 1 atmosphere and boils at 100 degrees Celsius, right? But again, the pressure is 1 atmosphere. If you increase the pressure, then water will boil at some higher temperature. If you decrease the pressure, the water will boil at some lower temperature. You see this red line here? All along this line, water is boiling, right? If you are here, that means boiling means what? Boiling means water and vapor are coexisting, right? When they are coexisting, that means we call it as boiling. Okay, when ice and water are coexisting, we call it as freezing. Okay, normal freezing point and normal boiling point are at 1 atmosphere pressure. I think this is clear. Now let's try to understand the concepts. Here you see this is a PT diagram. Now what you see, a red line here, this is the boiling curve, or you can say this is the liquid field and this is the vapor field, and this is the interface between liquid and vapor. Okay, now since the density is and volume is fixed, let's say we take an inclusion here, fluid inclusion, right? It will have some fixed value of bulk density, right? This is fixed. Let's say it is fixed at 0.8, right? Now whenever you heat this inclusion or you cool this inclusion, this thing will never change, right? Its density will be 0.8. All these numbers are in gram per cc. Okay, so if it is, let's say, at this high pressure and at this high temperature here, the inclusion is here. Now if we start decreasing the temperature, or you can say when we start cooling the inclusion, it will always remain on this line, because this line represents this bulk density, right? So these lines are also called as isocores. Isocores means fixed volume, and we know volume is fixed, right? And because it is closed system, density is also fixed. So this volume is represented, this volume here is represented by this isocore, which has a density of 0.8. Now when you are cooling this, it will come along this line, right? And it will meet the boiling curve at this point, right? So if it is in liquid field, the inclusion here will be completely liquid, because it is in the liquid field, it will be complete liquid. But when it comes to this point, a small bubble will appear in this, right? Liquid plus this vapor. So this small bubble will increase, and as you keep on cooling it, this size of this bubble will increase. But during whole process from here till here to back to this point, let's say you cool it down to the room temperature, till this point also the density will remain fixed, right? Throughout this, the density will be 0.8, right? If let's say if it was 0.9, it would have followed this isocore, hit it here and then moved in this direction, then the density throughout will be 0.9. Let's say if it was completely in the vapor field, that means the inclusion here was completely vapor, and you start cooling it, it will follow this isocore. Now you see, if it is complete vapor, the density is very less. As you can see, it is 0.1, 0.05, 0.15, which is very less density, right? And because of this vapor only, the density is very less. It will follow this isocore and it will hit the curve somewhere here again, right? And start cooling and follow this as the vapor reaches here, a small drop of liquid will form, right? And then it will keep on cooling in this direction. So this is the process, this is the trajectory or the path that the inclusion will follow. Okay, now whenever we are heating something, right, liquid will convert into vapor, right? But also the liquid will expand, right? And when we are cooling, vapor will convert into liquid and the liquid will also contract, right? Now liquid expanding will always be countered by liquid converting into vapor. So I'll come back to this, but before that you need to know this. The inclusions can have different proportion of liquid and vapor in it, right? We can have a very vapor rich inclusion in which the major portion is vapor and a small portion is liquid, and we can have a very liquid rich inclusion in which there is a small bubble of vapor and rest part is liquid, right? If now see this graph here, this one, the one on the right side, here there is temperature on the y-axis and the density of the inclusion on the x-axis. Now try to imagine if you have an inclusion that is vapor rich, right? It will have a density towards the lower side. Let's say it has a density somewhere here, right? 0.1. And if it is a liquid rich fluid inclusion, then it will have a density somewhere around here, let's say 0.8, right? In the previous graph it will be this isochore 0.8 and here it will be this isochore 0.1, right? Now as you start to heat this or cool this, see if I start to heat it, right? If I start to heat it, I will have different amount, the amount of vapor and liquid might change, right? Because as I'm increasing the temperature, the density will never change. It will always be a vertical line because density is fixed of the inclusion, right? But the amount of vapor and liquid will increase and decrease because you are changing temperature. So to keep the density same, right? Keep the density same, the amount of vapor and liquid in this inclusion might change. I'll explain that, but you have to understand here that the proportion during heating the inclusion or during let's say cooling the inclusion will not remain same. What will remain same is the density. Now because we are changing temperature, right, the amount of liquid will convert into vapor and vapor will occupy more space. As you are decreasing, the amount of vapor will become less, but the density will remain fixed. The only thing which is constant here is the bulk density. Okay, keep that in mind, right? This is also the same figure. This is the curve, right? Same curve as you're seeing on the right side, right? This is density, or you can say the amount of volume of liquid in the inclusion, right? If it is towards this end, it is 1.0, and if it is towards this end, it is 0. Same as density. Now, having understood this basic things, try to understand this graph. Let's say you have an inclusion at room temperature that has some amount of liquid and a vapor bubble, right? Now, what you are doing, you are heating this, right? First of all, because there are both phases present in it, liquid also and vapor also, it will always stay on this line till there are two phases, because this is liquid equal to vapor, or you can say the curve at which the boiling is happening, right? Both liquid and vapor are coexisting. That means it has to stay on this LV curve. Now this inclusion, let's say, has a density of 0.8 as given in this diagram. Now if you are heating it, two things will happen. Liquid will convert into vapor, right? Now by that logic, the size of this vapor should increase because liquid will be converting into vapor, right? As I have told you earlier, when you are heating anything, liquid is converting to vapor, but simultaneously the liquid is also expanding. Try to understand this now. If the liquid is also expanding, this vapor will have less area or less volume available, right? Now the thing is, liquid is no doubt converting into vapor, but the expanding here, the expansion of the liquid has more weightage, right? That means expanding will be more than liquid converting into vapor. So it's a combination of these two effects. When you are heating, actually liquid expansion is more. So liquid in the inclusion is occupying more space, and therefore less space is available for the vapor. So as you are heating, the size of this vapor will keep on decreasing, right, till the point where it becomes so less that it disappears. And the point it disappears, or the temperature at which it disappears, is called as the homogenization temperature. That means now everything is converted into one single phase, which in this case is liquid, right? Now if you keep on further heating it, it will just follow this isochore. It will leave this L equal to V curve, or the boiling curve, and it will go along this isochore. So, and it will keep on heating, right? And now since we have seen in the assumption that we have made that we know the origin, right, of this inclusion. If we know the origin, that means we know the trapping pressure, which is PT. Now if you know the PT pressure, you can draw a straight line here and it will cut the isochore somewhere. Let's say it is cutting here. Now from here, if you can calculate the temperature, right? If you draw a perpendicular here or vertical line, you will get this temperature. So this is the temperature at which the cavity was trapped during the formation of inclusion. Means this liquid was trapped in that cavity during the inclusion was forming, right? So this is the first motivation we had for this study. We wanted to know what is the trapping temperature, so we can calculate it like this, right? You start with the bubble inclusion at the room temperature and heat it. At some point it will be completely homogeneous. That means the bubble will go away, and if you further heat it, it will follow this isochore, right? Because this isochore is for this density, and you take it to a pressure which you know at which the inclusion has formed. Okay, from there calculate this. We can calculate this trapping temperature. This is the first thing that we calculate, right? If we cool this liquid, if we try to cool this liquid, it will just follow the same path in the backward direction. If you start cooling it from here, it will follow this isochore. When it hits this point, first bubble will form. If you keep on decreasing the temperature, the bubble will increase. Because see, when you are cooling something, what is happening? Vapor will convert into liquid, but also the liquid will contract. So though the vapor is going into liquid phase, because according to this, the size of the vapor should decrease, but liquid is contracting faster. So this has more weightage here, right? And when this has more weightage here, this bubble will increase in size as you cool it down to the room temperature, right? If you keep cooling it, the bubble size will keep on increasing. Okay, so this is the first thing. We calculate trapping temperature from fluid inclusions. Next thing is how to calculate the salinity. Now see, when we talk about salinity, I said the major contribution is from the NaCl, but KCl is also present. So the components here is NaCl, KCl and H2O. If you look at this ternary diagram on the right hand side, there is water, there is NaCl and there is KCl, right? Now this is the region where most of the fluid inclusions are present, right? But by what is the process by which we can calculate salinity? Okay, now let me break it very logically. You will be able to calculate the salinity only when all of the salt is dissolved in water, right? Salt plus water, right? This is salinity, right? Salt will never go in the vapor phase, right? So if there is a vapor inside an inclusion, inside this vapor bubble there will be no NaCl. NaCl will always be in the liquid part, right? But we have to make sure that all the salt which was present is completely dissolved here, right? And we have to know the salinity when the last crystal of the or the complete dissolution is happening. So how do we do that? Okay, so you understood. Now how to calculate that? So this is the process. If we take the top portion of this triangle, means this part, right? If you zoom into this part, there is a eutectic point here, there is a eutectic here, and there is a eutectic here, right? This line H2O KCl line is a binary eutectic between H2O and KCl. This point here is a binary eutectic between H2O and NaCl, and this is the ternary eutectic for the system that contains both NaCl, KCl and water. Now I'll do it for this binary part so that you can understand it easily. Okay, so look at this figure. Now let's say you have this inclusion, right, in which there is a solid crystal, there is liquid, there is some bubble, right? So bubble is there, but we are not considering it in this salinity calculation because we know inside the bubble there will be no NaCl. Okay, all the NaCl will be in the liquid or in the crystal form. Now you start with the crystal at room temperature. Okay, let's say this is room temperature, 25 degrees Celsius. Now when you are cooling it, when you cool this liquid, what happens is that it converts into hydrohalite. Now hydrohalite is NaCl.2H2O, right? It's a mineral. When you keep cooling it, it converts into, means it is not precipitating, rather it is solidifying. The whole in the liquid plus salt inside the cavity solidifies to form ice plus hydrohalite. So let's say you cooled it till this point. It will not follow this eutectic here or this path here, but it will completely go along this vertical line and hit this point at around minus 50 degrees Celsius, where everything is either ice or hydrohalite, right? Now what you do, you start increasing the temperature. So first what you're doing, you are freezing it, right? Practically when it reaches this point you should get salinity, but what happens mostly is that it doesn't give you salinity because it just solidifies it. But what we want is dissolution of salt in liquid, not solidification. Okay, so let me just clear this up. Okay, so now you have decreased the temperature, it has solidified and reached this point 2 where it is at minus 48 degrees Celsius. Now what we do, we start heating it again. Now when you are heating it, it will reach till this temperature, which is the eutectic temperature, right? And then as you move to this point, this ice will start to melt, right? Now ice will start to melt, right? And NaCl will start dissolving in that ice. Now it will move along this line as the temperature increases. You are heating it and it will reach at this point. At this point. Now this is the point where the last crystal of ice is melting. That means after this point it will leave the system, right? But we just want this point where the last ice crystal melts. When the last ice crystal melts, at this point in this inclusion, you have a vapor, a bubble, and liquid, right? And all the NaCl is now dissolved in this liquid, right? Now when it is dissolved in this liquid, at this point you want salinity. So now you can calculate salinity as you drop it down here, right? So this is the point you get at 5.5 weight percent. This is the salinity of the inclusion. Now if we look at this question which was asked in 2012, it says salinity of 3 different liquid inclusions in H2O NaCl system. That means in all of these inclusions there is NaCl along with water, right? So what is to be determined? We have to determine the salinity. Is to be determined by heating freezing experiments. Now the phase proportions of the inclusions at room temperature. Now all this condition is given at room temperature, right? Now how do you go about it? First thing, see, this is the cavity that has liquid plus vapor, right? That means NaCl right now is dissolved in this, right? But we don't know the temperature at which the last ice melted. We don't know this point here, right? And if we keep on heating it, the amount of vapor and liquid proportion will change, right? We want to know the temperature at which the last ice crystal melted. So first you have to freeze it. First we'll freeze it and then we'll heat it again, right? And when we heat it again, we'll get to this point. Similarly for this, here also first we have to freeze it and then heat it again, right? So that we can know what is the salinity when the last ice crystal has melted, okay? Because that is the proportion of liquid at which we want to calculate the salinity. If you keep on heating this vapor will decrease in size, right? So we don't want that liquid. We just want as soon as the last ice crystal melts, at that point we calculate the salinity, right? So for P we need to freeze it first, right? The freezing of P, so this option can be kept. Heating of P, this is wrong. Heating of all PQ and R, this is wrong, right? Freezing of P is correct, and freezing of R is also correct. So these two options, either B or C, freezing of R and freezing of P. Now let's look at Q. In Q we have this solid crystal also, right? That means this NaCl is not completely dissolved in this liquid phase, right? So we will not get correct salinity. Now first what we need to make sure is that this crystal gets dissolved in liquid, and NaCl will dissolve in liquid when we heat this inclusion, right? Because as you increase the temperature, more and more NaCl will keep on dissolving in liquid, right? So we need to heat the this Q inclusion, right? So it will be heating of Q. So it is heating of Q and freezing of R. See, C is also wrong because it is saying heating of R. We know we don't have to heat R. Both R and P first need to be freezed and then we have to do heating. And for Q, you have to heat it first so that NaCl gets dissolved in the liquid phase. Then only you can calculate the salinity. So the correct option here will be B, right? Heating of Q and freezing of R. Freezing of P is also correct, but this option is wrong because it says heating of R. Okay. The point is, you have to, the underlining thing here is that salinity is measured at the point when the last ice crystal melts. Right? And by looking at P and R, you cannot tell when the last ice crystal melts. So first you have to freeze it and then heat it again and see at this eutectic point the ice will start dissolving, right? And you will have both ice plus liquid. But at some point the last ice will melt, the last crystal of ice, and that is the point where we calculate salinity. So you have to freeze P and R, and Q you have to heat because and the solid NaCl crystal is still not completely dissolved in liquid, then there is no point in calculating salinity unless whole of the NaCl is dissolved in liquid. Okay, so the answer here will be B. Now this is another question that came in GATE, was two coeval primary aqueous biphase fluid inclusion. Coeval means that they are formed at the same time. Okay, now X, one inclusion is liquid rich and another inclusion is vapor rich, right? They occur in the same grain of the host mineral, so they are happening at the same time in the same mineral and in the same grain. That means the condition is same for both of them. At the time when the inclusion has formed, the condition is exactly same, right? Now it says, which one of the following situation most likely indicates the boiling of the fluid? Which of the situation will indicate that indicate the boiling? Boiling is the point where liquid and vapor are coexisting, right? Now there are these options here. Okay, so first let's understand the concept behind it, and then we'll see whether we can apply those concepts in this to find out the answer. Okay, now look at this curve. I'm explaining three different situations, and this will definitely help you understand what is happening. See, consider this point. It has a density of 0.322, right? Now 0.322 is a density of critical phase, means you can say critical density. Point is कि let's say you have a inclusion, there is an inclusion in which there is a bubble, let's say, and there is a bubble and there is a liquid. Now this is at room temperature right now, right? The density of this inclusion is fixed to 0.322 gram per cc. That means the bulk density is this point. Now see, as we have mentioned earlier, the density will not change. Density will remain the same because volume is fixed and the mass inside the inclusion is fixed. Now if you're increasing the temperature, this has to follow a straight line because density is fixed. Think about it. It has to follow a straight line, right? Now, it is in liquid plus vapor domain. Means liquid and vapor both are coexisting because it is on this L equal to V, or you can say the boiling curve. So it will follow this boiling curve, right? But because temperature is changing, liquid and vapor will change their proportion. Vapor will slowly become smaller because, again I am mentioning it, whenever there is heating, liquid will convert into vapor, but also the liquid will expand, right? So the expansion of liquid is dominating here, and therefore the bubble will slowly become smaller and smaller, and the last bubble will disappear at this point, right? And after this it will follow this isochore, right, with completely liquid phase in it. Bubble will disappear, but the bulk density will remain the same, 0.322. Now this is the critical case. Now, as I mentioned before also, you can have an inclusion that is a liquid rich, and you can also have an inclusion that is vapor rich. Okay, so we'll consider both this situation. Now let's consider a vapor rich inclusion shown by this point, which has a density of 0.1, and a liquid rich inclusion which will have a density of 0.8. First consider vapor rich inclusion. Now see, this is the room temperature, 25 degrees Celsius, 24-25 degrees Celsius. Now at this point, as you can see, the vapor is dominant, right? So at this point the inclusion will look something like this here and like this. There's a big vapor here and there's a liquid, right? Now what we are doing, we are trying to heat it. right? Now when we heat it, what will remain constant is the density, right? Density is fixed. Now density is fixed to a very small value here, which is 0.1. This should not change, right? The bulk density should not change. It will move means in this vertical direction. Now you see, look at this curve, this red curve, right? Now let's say you increased the temperature, you're increasing the temperature, and since it is in the liquid plus vapor field, it will always be on this boiling curve, right? Now you're increasing the temperature. You have increased the temperature, let's say you took it to 250 degrees Celsius, right? So around 250 degrees Celsius with 40, this is around this point. This is 250 degrees Celsius, right? When the inclusion has come to this point, if we can apply a lever rule here, right? This is the amount of vapor and this is the amount of liquid present in it. If you apply the lever rule, you can see this corresponds to the vapor present in this length, right? Corresponds to the amount of vapor present, which is more, and this length corresponds to the amount of liquid which is present, right? In the phase diagram, just as we apply the phase rule, lever rule in the phase diagram, similarly here. Now if I keep on increasing the temperature, you see this length is decreasing, right? That means the amount of liquid which is present in this inclusion is decreasing, right? And as it reaches this point is around 340 degrees Celsius, right? Or 330 degrees Celsius, this point. At this point, when the inclusion reaches this point, you see the liquid has disappeared. If you apply lever rule here, this whole thing is now vapor. This length is 0 now, right? That means at this point, the last liquid drop will disappear, right? It will be something like this. Whole thing will be vapor and there will be small liquid here, and it just, the last liquid disappears and it will come in the vapor field. Now if you keep on increasing the temperature further, it will follow this curve and it will be a complete vapor. Means the inclusion will look like this, big bubble inside it without any liquid. This is the first case. In another case, we have a liquid rich inclusion, right? Which has a density of 0.8. Again, you are starting with 25 degrees Celsius. So you have inclusion like this, in which there's a big bubble, there's a liquid portion is big, so there's a small bubble and majority is liquid, right? Now you are again increasing the temperature, so the temperature will move like this, it will increase like this, right? Both liquid and vapor. But you see again, if you apply lever rule, right, this is the amount of vapor. This length at any temperature, let's say temperature is this, at any temperature this length indicates the amount of vapor which is present, and it is keep on decreasing. It is decreasing, and as it reaches 250 degrees Celsius, you see at this point, or in figure it is this point, 250 degrees Celsius, 20, 40, 50. So at 250 degrees Celsius, when the inclusion reaches here, the amount of vapor you see is very less. The whole length is now corresponding to the amount of liquid which is present. So this will be the last bubble, or the smallest bubble will keep on decreasing in size and a small dot will remain, and after that it will follow this isochore, because now it is completely liquid. It has to, if it is completely liquid now, after this point it will leave this curve, boiling curve, and go into the liquid domain, or in this graph it will go through along the isochore, keep on heating, and it will keep on following this path, right? Now coming back to the question says these are two coeval primary aqueous biphase inclusion. Coeval mean they are forming at the same time, and the inclusion that are formed is liquid rich and vapor rich. That means there was liquid also and vapor also at that point, means it was boiling, right? At that time, the inclusion is formed, in which one inclusion has a vapor rich thing and one inclusion has a liquid rich component, right? But because they are forming at the same time in the same mineral and in the same grain, it has to be the same point on the boiling curve, right? Let's say the liquid rich was or you can say the liquid rich inclusion was having a density 0.75 and vapor rich inclusion had a density of 0.2, let's say, for example. But they were formed at the same time, right? And now you are finding them at room temperature, right? So one is here and another is here, or let's say one is at 0.75, one is at 0.2. But point is ki they are formed at the same temperature, right? Because they are formed at the same grain in the same mineral at the same time, so it has to be the same temperature. So when you heat them, they will reach to the same point. Both the inclusion will reach to the same point. This will be a small bubble and a liquid, and the another will have a big bubble and a liquid, a small liquid portion. As you keep on heating, it will move along this isochore, and this vaporage will move along this isochore, right? This one is X and this one is Y. So on heating, the Y will completely convert into vapor phase and X will completely convert into the liquid phase. Means that is homogenization, but the temperature will be same, right? Because that is where they are formed, right? So the correct option here, X homogenizes to liquid, this line, this phrase is correct, and Y homogenizes to vapor, this is also correct, at different temperature. This is wrong, right? Because they are forming in the same time in the same mineral and in the same grain during boiling, so it has to be the same temperature. It has to be. Both homogenizes to liquid, this is wrong. Vapor rich will homogenize to completely vapor, as we have seen. Liquid rich will completely homogenize to liquid. Both homogenizes to vapor, this is also wrong. X homogenizes to liquid, this part is correct. Y homogenizes to vapor, this is correct, at the same temperature, this is also correct. So in this question, the answer will be D. Make sense? So as you are heating a liquid rich bubble, remember, liquid rich inclusion, the bubble will keep on becoming smaller and smaller. And if you are heating a vapor rich bubble, the liquid will keep on, or the vapor will become bigger and bigger, so that the density remains constant. Density will not change, right? And if they are formed at the same point, they will homogenize also at the same temperature and then go in their respective, along their respective isochores. So this is the concept behind fluid inclusions. I hope you understood it. Thank you very much.